Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
So according to the definition, the oxidation number of an atom in a molecule or an ion is defined as the number of charge it would carry if electrons were completely transferred. So this means what? Suppose, let me give you an example. Sodium, which is a metal, it has the capacity to lose electron. So if it loses electron or if it transfer the electron, so the charge that would present on the sodium would be +1, because by losing one electron it will get a charge of +1 on it. When I talk it about lithium and potassium, they both are belonging to S block, and as you know that the S block has the capacity to lose one electron. So if they lose one electron or if they have transferred one electron, then the charge present on that metal respectively would be 1. Suppose I am talking about lithium. So lithium is belonging to S block element and it has the capacity to lose electron. So it will lose one electron and it will gain positive charge on its oxidation number. And talking about chlorine atom. So chlorine atom has the capacity to take electron. So if chlorine atom takes one electron, then the charge present during the transfer of electron by chlorine will be -1. This -1 or this 1 minus represents that the chlorine atom has accepted one electron. So let me tell you what is the difference between the charge and how we represent oxidation number. Usually when we say -1, it represents that the charge present on a particular atom or a particular molecule or an ion. When we talk 1 minus, this represents the oxidation number. So let me tell you by giving a example of each and every one. So these are the examples as being mentioned and are being represented on your screen. So it says that the sodium has a oxidation number of 1 plus. In this case we could have written +1, but the +1 will indicate the charge that is present on the sodium, while 1 plus means the oxidation number of the sodium. And as you know, the oxidation number changes for D block elements and the charge remains the same on a particular atom or ion. So in this case I am talking about lithium. Again it is 1 plus. For potassium it is 1 plus, and for oxygen it is 2 minus. For fluorine it is 1 minus. For chlorine it is 1 minus. And this is not necessary that chlorine will have 1 minus oxidation state, because as you know that it contains many electrons in the p block in its p orbital. So therefore the electrons can be transferred by gaining or can be transferred by losing. So according to that, the oxidation number of chlorine can be 1 minus, can be 2 minus, can be plus, can be 1 plus, can be 2 plus, can be 3 plus. So I have written is just a common oxidation state of chlorine that it shows. Oxidation state and oxidation number, the both are same. So in this case Br is showing 1 minus oxidation number, while in case of hydrogen it shows 1 plus in a normal or in a simple molecules. Hydrogen shows 1 plus oxidation state, but it shows 1 minus oxidation state in hydride molecules. So these are the few examples of the elements that we are going to learn based on the oxidation number, and with the help of this we could also find out the oxidation number of other elements present in the molecule. So let us see by giving an example. So this is the question which is based on determination of oxidation number of an underlying species element. In this case this is PF6 minus, which means the overall charge present on this molecule is minus. and we know that the oxidation number of the fluorine is 1 minus. Therefore, the oxidation number of F is nothing but 1 minus. And we don't know the oxidation number of phosphorus here, and we have to calculate, or we have to determine that what would be the oxidation number of phosphorus in this molecule. So let me assume that the oxidation number of phosphorus is X, and we also know that the charge present on this molecule is -1. So therefore, the charge on molecule is -1. So by the help of this, we could calculate that what would be the oxidation number of phosphorus. So phosphorus is present only one time, so I could write 1 into X. This X represents the oxidation number of phosphorus, plus I have 6 times that of fluorine atoms, that is, and which has an oxidation number of 1 minus, and ultimately the charge present on the molecule is -1. So therefore, 1 into X is nothing but X, plus 6 into oxidation number of fluorine is 1 minus, which will make an answer of X plus -6 into -1 is equals to -1, which means X is equals to -1 plus 6. So this is the value of X has been calculated as +5. But while writing the oxidation number, we represent it by 5 plus. So therefore, the ultimate answer is the oxidation number of phosphorus in PF6 minus is 5 plus. So this is how we have calculated the oxidation number of phosphorus. Let me give you another example. So we are going to do various examples based on the few concepts that would have been changed. This was a very simple example that you have calculated, but there would be some complex too. So let us see how can we calculate it. I have mentioned another example. In this case, I, that is iodine, is being the underlying species. And how can we calculate? Let us see. In the whole species, as you can see, or in the whole molecule, as you can see, there is no charge present on it. While we also know that the oxidation number of sodium is 1 plus, while the oxidation number of oxygen, I represent this oxygen as oxy, so you should not be confused between what is O and what is 0. I would write it as 2 minus, and the charge on the molecule is 0. So now what we are going to do is we have to calculate that what, or we have to determine that what would be the oxidation number of iodine in this case. So how can we write it? We could write that the sodium is present only one time, so I'll write it 1 times Na, plus iodine is also present 1 times, but in this case I would represent the oxidation number of iodine as X, plus there are 3 times of oxygen atoms. I would represent it by oxy, which has a charge of, which is 0. Now, as we know that the oxidation number of sodium is 1 plus, while that of the iodine atom is X, and for oxygen it is 2 minus, which is equals to 0. So this will give an overall answer as 1 into 1, that is 1, plus X plus minus 6 is equals to 0. So in this case, X will be nothing but this 6 will go over there, so it will become plus 6, while the 1 will go over there, it will become minus 1. So ultimately we'll get an answer as plus 5. But the oxidation number is represented by 5 plus, so therefore the oxidation number of iodine atom in this molecule will be 5 plus. So let me give you another example also. We are going to do various examples based on this. So this is another example which is in which boron is being the underlying species, and we have to calculate the oxidation number of boron. So I could write, and as you can see, that is there is no charge present on the whole molecule, so that therefore the overall charge of this molecule is 0. But I have considered the oxidation number of sodium is 1 plus, while that of the boron I would consider it as X. And in this case, it should be clearly noticed that this molecule is nothing but an hydride of sodium and boron. So therefore, in this case, the oxidation number of hydrogen, that is, the oxidation number of hydrogen can be plus 1 also, that is 1 plus and 1 minus also. So in this case, since this is a hydride molecule, so therefore the oxidation number of the hydrogen in this case will be 1 minus. So by the help of the equation, we could calculate that there is only 1 time sodium which is present, plus 1 time boron, plus 4 times that is of hydrogen atoms, which is a hydride molecule, and the overall charge is 0. So the charge on the sodium is now found to be plus 1. So therefore 1 into plus 1 is nothing but 1 plus itself, plus boron I have taken the value as X, and hydrogen in this case is 1 minus. So therefore the overall charge can be written as 4 minus, which is equals to 0. And since we are relating it with charge, this 4 minus will be minus 4 itself. So what we are going to do is, we are shifting the force towards that side, so this would be this minus 4 towards that side, so this would be plus 4, and this 1 towards that side, so this will be minus 1. So therefore X will have a value of plus 3. But the oxidation number is represented by 3 plus. So therefore the oxidation number of boron in this case, or in this molecule, will be 3 plus. So let us take another example. This is of different type, but we have to do it very carefully. So in this thing, this vanadium oxide molecule has a 4 minus charge. So therefore we could write the oxidation number of vanadium. In this case, we have to find it out, so we'll take it as X. So therefore the oxidation number of vanadium will be X, while the oxidation number of, for this case, oxygen atom I could represent by oxy, is 2 minus, and the charge on the molecule is 4 minus. In this case, we should notice that the oxidation number can be not only for atom, it can be for a molecule also. So in this case, the oxidation number of the molecule is 4 minus, while the charge is minus 4. So we could write this charge as the oxidation number of the molecule also. So let us calculate it. Therefore, 2 times vanadium plus 7 times presence of oxygen, that is oxy, and the overall charges or the overall oxidation number of this in this case is 4 minus. I could represent it by minus 4 also, just for an instance to for a better solving this problem. So therefore 2 into vanadium, that is represented by small x, plus 7 into oxy. This oxy has a oxidation number of minus 2. So I could represent it this way, and overall charge is minus 4. So therefore 2 into x, this minus 4 will be added with the 14. So therefore this will be 10, and the value of x that is being found, that is 14 minus 4, that is 10, and this 10 divided by 2 is nothing but 5. And while mentioning, we have mentioned the vanadium, we have not mentioned the oxidation number of V2, we have mentioned the oxidation number of V. So in spite of having the value 2, we can, so in spite of having the underlying species as V2, we should find the underlying species oxidation number as a single atom. So in this case, the oxidation of vanadium in this case is 5 plus. So moving towards the next one. This is a manganese trihydroxide molecule, in which again you can see there is no presence of charge. So we could write in this way that the oxidation number of manganese, I would take it as X, and we also know that the oxidation number of hydrogen is 1 plus, while the oxidation number of oxygen, I would write it as oxy, is equals to 2 minus. So eventually I could write it as 1 into manganese plus there are presence of 3 oxygen molecules. So therefore 3 into oxy, as well as there is presence of 3 hydrogen molecules, 3 hydrogen atoms and 3 oxygen atoms in the molecule. So therefore 3 into hydrogen, and the overall charge is 0. That is, overall oxidation number is 0. Therefore X plus 3 into minus 2, that is minus 6, plus 3 into 1, that is 3, which makes a value of X is equals to 3. But the oxidation number is represented by 3 plus. So therefore the oxidation number of manganese in this molecule is 3 plus. And moving towards the last numerical, or the last example. So moving towards the last example that we are going to do, this is a very critical one. So let me give you an idea how to solve this, and let me tell you, this molecule are said to be complex or coordination compounds. So we have to calculate the oxidation number of Fe present in the complex. So how can we do that? First of all, it's a very simple process to do. That is, we know that the oxidation number of potassium is +1, but it is not present in the complex molecule. That is, it is not present in this region, in this complex molecule. So therefore what we are going to do is, we are calculating the oxidation number of 3 potassium. 1 potassium has a value of +1. So therefore 3 potassium will overall have an oxidation number of +3. So if the complex will have a charge of +3 on potassium, then it will have -3 charge on the complex, or the complex will have an oxidation number of 3 minus. So therefore, we have a concern for this Fe, this iron. So what we are going to do is, iron which is present 1 times, so therefore 1 into Fe plus cyanide is being represented 6 times, and the overall charge or the overall oxidation number of this molecule or this complex now is -3. So Fe has the value X, while it has been known that the oxidation number of cyanide is nothing but -1. So therefore 6 into -1 will be, we'll get an equation of +3, and hence the oxidation number of iron in this complex is 3 plus. So this is how we have calculated various oxidation number of various atoms present in the molecule by doing the oxidation number method. I hope you have got an idea how to solve this kind of determination of oxidation number. So thank you friends for watching this video. I hope you have liked this video, and please don't forget to subscribe Ekeeda channel. Thank you so much.